Welcome to the Deep Dive, the shortcut to becoming truly well-informed about the invisible systems that power your digital life.
Today, we are profiling the architectural DNA of really the biggest computer system ever built, the warehouse scale computer, or WSC.
And this isn't just about, a rack of big servers. This is about the entire infrastructure, the data centers that serves billions of users globally every single day.
The foundational concept driving this whole analysis is it's simple, but it's really profound. The data center is the computer.
The data center is the computer.
Exactly. But if you treat an entire building with tens of thousands of machines as a single computational unit, well, how do you even begin to diagnose its performance bottlenecks?
Right.
This deep dive is based on a really unprecedented study. They profiled over 20,000 live production machines across thousands of applications over a 3-year period.
That scale is just it's staggering. And the mission here seems so vital because we have to move past this older sort of conventional wisdom.
You mean like optimizing hardware just based on spec benchmarks?
Exactly that. We need to analyze where the CPU cycles are actually being spent in the real world on live services.
That's absolutely right. We're hunting for the truth that's hidden inside this enormous system. We're looking for the common architectural characteristics, the surprising and shared software patterns, and the key microarchitectural demands that have to dictate how the next generation of server silicon is designed.
So, if you need to quickly grasp what truly drives the performance decisions at giants, like the major cloud providers, this is your blueprint.
It is.
We are going to show you precisely where the computational time goes and, crucially, how architects plan to use this knowledge to build faster, more efficient platforms. Let's unpack this massive study, starting with the very definition of what makes a WSC unique.
Sounds good.
So if the WSC is the computer, what differentiates it from, say, the server farms of the 1990s, or even a more traditional enterprise cloud setup?
It really all comes down to internet scale, distribution, and economics. Traditional server design, it prioritized maximizing performance for maybe a single task, or ensuring, bulletproof reliability for just a handful of applications.
Right, like a big database server.
Exactly. WSCs, however, are fundamentally designed for performance and cost efficiency across thousands of nodes all at once. Their design emphasizes system-wide throughput, redundancy, and efficiency above literally everything else.
And we've definitely seen this massive migration toward this model over the last decade. It feels like everything is moving in this direction.
It's a complete structural shift. Computing has really moved to two extremes. On one side, you have these massive WSCs in cloud computing, managing these complex, often really bursty back-end tasks.
And on
the other, you've got the highly optimized mobile devices and the whole Internet of Things. But the critical thing to remember is that the mobile and IoT ecosystems are almost universally supported by that WSC backend.
So the WSC is the massive engine that's powering the entire global cloud infrastructure.
That's it. It's the engine room.
And that massive engine, it has to rely on intensely distributed software. So let's look at that environment. We're talking about multi-tiered services, right?
Yes. The WSC operates entirely through distributed multi-tiered services. And while, modern engineers call these microservices, the core architectural concept actually predates that term by quite a bit.
So the idea has been around, even if the buzzword hasn't.
Right. Each service is a tightly defined component that communicates only through very standardized interfaces.
So the communication isn't just raw data packets flying around, it's highly, highly structured.
It absolutely has to be, especially given the scale and the complexity we're talking about. The communication is handled almost exclusively via remote procedure calls, or RPCs.
RPCs.
This strict reliance on RPCs enforces this necessary structure, and it ensures that all the requests and all the responses are universally standardized across the entire fleet.
And this standardization, it must rely on specific algorithms and data structures. This seems to be a key focus of the system design.
Exactly. The data serialization algorithm is absolutely central to the entire system. At Google, this format is specifically protocol buffers.
Protocol buffers?
It's the lingua franca for data transport. This standardization ensures this massive internal cohesion and speed, but, and this is a big but, it generates an enormous amount of computational overhead. A fact we're definitely going to analyze closely later.
And when you have hundreds of these services all interacting for just a single user query like a complex search or retrieving personalized content performance, really comes down to the slowest component in that chain.
Precisely. In the WSC, latency is the defining performance metric, particularly what we call tail latency.
Tail latency, so not the average time, but the worst case time.
Exactly. It's the time it takes for the slowest requests, the 99th or maybe the 95th percentile requests to complete. Think about it. If a single complex transaction requires, say, 100 parallel RPCs to fetch data, and even one of those 100 is slow, the entire user request is blocked.
The whole thing grinds to a halt waiting for that one straggler.
Right. And so engineers spend an enormous amount of effort applying really sophisticated algorithms and queuing techniques specifically aimed at reducing that tail latency because it directly impacts the user experience.
Okay, so we have this massive distributed system, and it's defined by latency. How on earth do you even begin to profile 20,000 machines continuously for 3 years without crushing the very performance you're trying to measure?
That's the million-dollar question.
And that's where this Google-wide profiling or GWP system comes in.
It is. GWP is the critical piece of infrastructure required to make this longitudinal study possible. The core premise is statistical.
Okay.
It's all about low overhead random sampling. You target a small fraction of the server fleet at any given time, and then you randomly sample the execution time within those specific machines.
If you can't profile everything all the time.
You can't. The observability overhead would make the data totally irrelevant. You'd just be measuring the cost of your own measurement tools.
So what are the mechanics of this sampling? How do they actually gather and analyze the data?
The GWP collectors, they randomly select a really tiny subset of the server fleet. I mean, maybe a fraction of a percent daily.
A very small sample.
Very small. Then they trigger profile collection using lightweight Linux tools like perf, which is great because it just captures snapshots of the CPU state and the call stack with very low impact.
And then the crucial step is making sense of that raw data.
That's the crucial step. It follows immediately. They symbolize the collected call stacks. This means matching the raw memory addresses that were captured during the profile with the corresponding function names and the source code locations in these massive binaries.
And where does all that symbolized data end up?
It's aggregated into a huge centralized data structure. Specifically, they use a Dremel database. For those who aren't familiar, Dremel is a proprietary query system that's designed to analyze colossal nested data sets really quickly.
So that aggregation is what allows them to see the forest for the trees.
It lets them look across the entire fleet and millions of samples to find the real patterns, rather than just getting lost looking at one machine or one specific application.
Now, I noticed the scope of the study focuses really heavily on C++ code. And given the sheer diversity we're talking about, Python, Go, Java, Y, the specific focus on C++ code.
It's a matter of computational physics, really. While those high-level languages like Java, Python, and Go are very popular, and they account for huge amounts of lines of code in the WSC.
Right, there's a lot of it being written.
A ton. But C++ is the dominant language that consumes the vast majority of the actual CPU cycles. The really highly optimized, latency-critical, low-level infrastructure, things like networking stacks, data management, the core search engine itself, that's almost all C++.
So if you want to know where the time is being spent, you have to look at the C++ B.
You have to. Focusing there allows for the cleanest architectural study of actual computation time across the entire production fleet.
Okay, let's tackle the heart of the architectural analysis then. The top-down performance analysis algorithm. This seems to be the intellectual breakthrough that allows them to measure these stalls so accurately on modern, highly complex chips.
It absolutely is. And we need to remember why the older metrics just don't work anymore. Historically, we relied on metrics like, say, MPKI, that's misses per kilo instruction, to measure cache efficiency.
So if your L1 instruction cache had a high MPKI, you'd assume it was a bottleneck.
Right, that was the assumption. But I've heard you mention before that on a modern out-of-order processor, those raw counts can be really misleading.
That's the problem. A modern chip might see a high MPKI, but because it has these deep internal buffers and it can execute instructions out of order, it can often hide that latency.
So the miss happens, but the processor just works on something else while it waits?
Exactly. The high cache miss rate, in that case, might not actually degrade the end performance at all. I like the analogy of counting accidents on a highway. If they all happen at 3 a.m. and don't slow down the rush hour commute, does the raw accident count really matter to the average driver?
That's a great way to put it. So the top-down methodology, it looks for the cost of the stall, not just the occurrence of the miss.
Precisely. The core method reconstructs these approximate CPI cycles per instruction stacks. It calculates the cost of stall events and cycles, which is the ultimate currency of performance.
So it quantifies the end cost. It tells the architect, look, this specific cache miss is actually costing the program 15% of its total execution time, regardless of how much clever buffering is trying to hide it.
So how do they categorize all these potential stall cycles in a systematic way? It seems like there could be hundreds of reasons a CPU stalls.
There are, but they use a really clever dividing line. The microop or op queue in the out-of-order processor, every potential pipeline slot is classified into one of 4 top-level categories.
Okay, what are they?
So think of the processor as having a fixed number of slots it can work on per cycle. First, you have retiring. These are the good cycles, where instructions are completing their work. This is what you want to maximize.
That's the useful work.
That's the useful work. Second, you have front-end bound. This means the core is just sitting there waiting for instructions. It points to problems with instruction fetching, prefetching, or instruction cache misses.
What's third?
Third is bad speculation.
Oh.
This is really costly work that the processor did, but then has to throw away, usually because of a mispredicted branch.
And the last one must be about data.
Exactly. The fourth category is back-end bound. This is when the execution units are stalled waiting for data. Typically, that means data cache misses or just general memory access latency.
So by using this 4-part method, they get this incredibly accurate picture of the microarchitectural weaknesses. And now we can transition to what these weaknesses actually revealed across the entire fleet.
Yeah, and the findings are pretty shocking.
For years, the story of the largest tech companies was that they were built around 1 or 2 massive applications, like search or advertising delivery. Let's start with 2.1, extreme workload diversity. What did the profiling reveal about the distribution of work?
Well, the findings definitively killed the killer app myth. It's just not true anymore. When you look at the entire WSC fleet, no single application dominates.
Not at all.
The hottest single application accounts for only about 10% of the cycles.
Only 10%.
Yeah.
That completely flies in the face of what I think most people assumed was driving these infrastructures.
It really does. It shows the sheer maturity and complexity of the platform. You need a long tail of 50 different applications just to account for 60% of the total WSE cycles.
50 applications to get to just over half the work.
The diversity is enormous, and this presents a massive challenge for hardware designers who just want to find one specific thing to optimize.
And it's not just diverse. The study showed it's actually getting more diverse over time.
That's the critical longitudinal trend. Over the 3-year study period, the fraction of cycles covered by the top 50 binaries decreased by nearly 5 percentage points per year.
Wow.
Yeah. It dropped from 80% coverage in the early period of the study down to less than 60% towards the end. Hardware optimization is essentially chasing a moving, diversifying target.
You can't just design silicon for application A.
Right. Because in 18 months, application A might only consume 5% of the total cycles. The ground is constantly shifting.
So if you can't optimize at the application level, what about inside the applications themselves? This brings us to 2.2, flat execution profiles within applications. Do these massive binaries have clear hotspots, 1 or 2 functions doing all the work?
Again, the answer is really counterintuitive. These individual binaries are already extremely mature. They've been highly optimized by generations of software engineers.
So the low-hanging fruit is gone.
It's long gone. They show very, very flat execution profiles. The study highlighted the example of Search 3. In that binary, the single hottest function was responsible for only 6.3% of the cycles.
Only 6.3%.
And to find 80% of the execution time, you had to combine the cycles from 353 different functions.
A flat profile like that means optimization efforts are just going to hit diminishing returns almost immediately.
Exactly. It stands in really sharp contrast to some of the early benchmarks, like Cloud Suite Data Analytics, which had these really steep profiles where maybe 3 functions would account for 65% of the execution time.
Not anymore.
Not in the WSC. These flat profiles mean that per application, human-driven optimization engineering is incredibly costly and inefficient. The returns just aren't there.
So if you can't optimize the application and you can't target the hotspots within the application, this forces the focus down onto the lowest common denominator shared across all programs.
It has to.
This leads us to 2.3, quantifying the data center tax. This is, I would argue, the most profound insight of the entire study.
It really is the unifying theory of WSC performance. Despite the staggering diversity at the application layer, all of those different services, they still have to talk to each other, they have to serialize data, and they have to manage memory.
The basics. The basics. And these common low-level building blocks, what they call the data center tax, they persist across every single application, consistently consuming between 22% and 27% of all execution cycles across the entire fleet.
Almost a third of the world's largest computing platform is spent on operational overhead, completely independent of the actual product logic. That's a massive, addressable drain on resources.
It is. And because these routines are mature, they're standardized, they're widely used, and they change very slowly, they are the ideal candidates for hardware specialization in future server systems on chip, or SOCs.
This 27% is the low-hanging fruit for the architects.
It's the biggest target they have.
Let's dedicate some serious time to truly understanding the components of this tax, starting with protocol buffer management, the serialization, and deserialization. Why is this so computationally expensive? Well, protocol buffers are the glue. They're the structure that's imposed on all the data. So every single piece of data that's transmitted between services has to be encoded into a stream, that's serialization, and then rebuilt into memory structures on the other side, deserialization.
And the code that does this is automatically generated.
Yes, the code responsible for this is often automatically generated based on the schema definition for the data.
So the inefficiency isn't necessarily from, like, poor logic written by a human, but it's the sheer volume and the architectural constraints of that generated code.
Precisely. The generated code often results in these complex, repetitive memory accesses and a real lack of data locality. It's because it's manipulating data fields one by one, rather than in these nice, big, efficient bulk operations.
This constant marshalling and unmarshalling.
It accounts for the majority of the protobuf tax. And the architectural direction here is pretty clear. Dedicated accelerators. It's similar to what was proposed for high-speed XML parsing decades ago.
Where would these accelerators live?
They need to reside extremely close to the memory or the last level caches to perform that computation near the data before it even has to enter the main CPU pipeline.
Okay, next component. Remote procedure calls, the RPCs. Since every single communication is an RPC, this has to be a heavy load.
RPCs are truly ubiquitous, but the tax here is layered. About a third of the RPC tax cycles are spent on control functions.
What does that include?
Things like load balancing, setting up the connection, necessary failure detection, and, of course, a significant amount of cryptographic overhead for security.
And the remaining two-thirds of the RPC tax.
It's just simple data movement. Once the RPC connection is established and that protocol buffer payload is ready to go, the system still spends an inordinate amount of time just moving that data from one memory location to another.
So it's pure low-level overhead that should be architecturally minimized.
It is. And the hardware suggestion here isn't something exotic like a cryptographic accelerator. It's for generic data movement acceleration, simple, fast silicon that's just dedicated to bulk memory transfers.
Moving on to compression. This accounts for roughly a quarter of all the tax cycles. That's huge.
It's a huge drain because absolutely everything is compressed data in memory, data in logs, network traffic. It's all general-purpose lossless compression, primarily using algorithms like Snappy.
And Snappy is designed for speed.
It's designed for extreme speed because it has to run on the CPU.
So if the algorithms are already optimized for speed, where is the hardware opportunity?
Well, the opportunity is twofold. First, just offloading the existing Snappy-like algorithms to specialized accelerators reduces core congestion, which is a good thing.
Right?
But more importantly, it offers a crucial trade-off. Currently, software uses these fast compression algorithms because running them on the CPU is so costly.
Okay.
If dedicated hardware could execute algorithms with better compression ratios at the same or even higher speed, the WSC could significantly save on storage space and network bandwidth everywhere else. It leads to these cascading system-wide cost benefits.
So the 27% computational tax is actually acting as a constraint on the type of algorithms they can even think about deploying.
It is. That's a great example of the architectural constraint imposed by the cost of software.
Let's talk about memory allocation. How is this still a massive component of computation in, well, today's world?
It's the complexity of modern operating environments. We're not talking about a simple malloc anymore. Production WSC code uses these highly sophisticated allocators that employ complex, often recursive, data structures.
And why? What are they trying to do?
They're trying to manage thread local heaps and avoid locking contention at all costs. But to do that, they have to interact heavily with the operating system's memory management unit.
So even after decades of software optimization, memory allocation remains this really thorny issue.
Yes, the constant need to manage memory at this scale, I mean, the sheer number of allocations and deallocations per second, it just introduces substantial overhead. The cycles spent here are high enough that the researchers suggest investigating hardware allocators is actually warranted.
Even though it would be incredibly difficult to implement those complex policies in immutable silicon.
Even so, the potential payoff is just that big.
And finally, we hit data movement. We're talking about basic functions like mecpy and memmoose.
We are talking about explicit named copies. These library functions alone account for 4% to 5% of all WSC cycles.
4 to 5%.
And that is a conservative lower bound. It's a floor. Because it doesn't count all the implicit data copies that the compiler or the system might perform without calling an explicit library function.
To realize that 4% to 5% of the computational power of the modern cloud is dedicated purely to explicit copying is genuinely shocking.
It is, and it points directly to the need for some pretty radical architectural proposals, the idea of row clone, for example.
What's that?
It's the concept of performing bulk data movement and initialization directly within the DRAM chips themselves, completely bypassing the core. You move the computation to where the data already resides.
That's a paradigm shift.
It is.
Before we leave the tax section, we have to acknowledge 2.4, the kernel tax. It's everywhere, but the study treats it a bit differently.
That's because it's absolutely immense. WSC applications spend nearly a fifth, around 20% of their CPU cycles in the kernel.
20%.
But the researchers are very clear. This is not considered acceleratable tax.
Why not? If it's a 20% overhead, why can't we just offload it to some specialized hardware?
Because the kernel is just too complex, it's too large, and it's constantly evolving. It manages fundamental OS functions, security, file systems, scheduling. It cannot be neatly swapped out for dedicated static silicon.
It has to be optimized in software.
It has to be.
Yeah.
But it represents an unavoidable cost of running a secure concurrent operating system in this scale.
And the data revealed a prime target for continued software tuning within the kernel, the scheduler.
Yeah, even after immense tuning efforts over the years, the scheduler alone still accounts for more than 5% of all data center cycles.
And the challenge there is just structural.
It is. A 90th percentile machine in the study was running about 4,500 concurrent threads. Managing that many threads, deciding who gets the next execution slice, handling the context switches, it introduces this enormous, unavoidable overhead simply due to the sheer concurrent scale. 5% is the price you pay to run 4,000 threads efficiently.
So we've established that nearly half of the available cycles are spent on necessary overhead, 27% for the data center tax, and 20% for the kernel.
A huge chunk of the pie.
Now let's look inside the processor core itself and analyze why the remaining cycles are stalling. Section 3.1. Overall low core utilization.
This is a universal finding across the entire fleet. WSC workloads exhibit very low instructions per cycle, or IPC.
How low are we talking?
The average IPC is about half the geometric mean for the SPCent benchmarks. In fact, WSC performance is more comparable to the most pathologically memory-bound spec benchmarks, like 429.mcf.
So despite all the billions of dollars spent on this high-performance silicon, the CPU cores are sitting idle a huge amount of the time.
They are starved. The top-down analysis confirms this directly. When you look at those four categories we talked about, retiring, front-end bound, bad speculation, and back-end bound, very, very few microops are actually retiring.
Most of the time is spent stalled.
Most of the time is spent stalled, just waiting for either instructions or data.
Let's break down that stall time then, starting with 3.2, back-end pressure. Is the WSC running out of data bandwidth? Is that the problem?
This is where the study delivers its most impactful architectural shockwave. For decades, the conventional wisdom in data center architecture has been to over-provision memory bandwidth.
Right, assuming these high-throughput workloads would constantly be stressing the memory controllers.
And the reality,
It's not that.
it is overwhelmingly a latency problem, not a bandwidth problem. Data cache behavior is the single dominant factor in stall cycles, accounting for 50% to 60% of all cycles. That's over 80% of the back-end bound slots.
So the cores are just waiting for data loads to complete through the cache hierarchy? Wait, I need to pause on that bandwidth finding. How utilized is the memory bandwidth, actually?
The utilization is universally low. They measured the median memory bandwidth utilization across the entire fleet at a shocking 10%.
10%.
10%. And even the high watermark, the 95th percentile, was only 31%,
And you contrast this with CPU utilization.
which is often in the 40% to 70% range. The memory system is massively, dramatically over-provisioned for bandwidth.
That is a staggering piece of information. That means a huge amount of silicon area, power, and money is being wasted on memory controllers and channels that are almost always idle.
It fundamentally changes the design equation. If memory latency is significantly more important than bandwidth, then architects can and should make a major design trade-off.
What's the trade-off?
Reduce the number of memory controllers. That freed up silicon and power budget can then be redirected to components that actually matter, like enlarging the caches, adding more cores, or integrating those specialized data center tax accelerators we talked about.
The warning here must be explicit then. Do not base WSC hardware design on benchmarks that focus on throughput.
Absolutely. SpecRit results, for example, focus on bandwidth, which we now know is plentiful. The entire production fleet confirms that memory latency is the real performance constraint.
So we have these cores that are stalled over 70% of the time waiting for data, but they still need to be powerful for when the data does arrive. Let's discuss 3.3 bimodal instruction level parallelism, or ILP.
Right. The WSC applications do not execute in a steady, predictable flow. They exhibit this very mixed execution pattern.
Describe it for me.
It's long stretches of stall, waiting for data dependencies, and those are interspersed with these intense, short bursts of computation where the core needs to execute many instructions simultaneously.
Can you quantify this sprint and wait behavior?
Using an Ivy bridge core as a reference, which is 6 wide, the numbers are pretty stark. 72% of execution cycles show very low ILP, meaning the core only managed to issue 1 or 2 microops in that cycle. However, 28% of the execution cycles show high utilization, keeping 3 or more functional units busy.
That 28% is crucial, right? It means the core needs to be ready to execute across its wide pipelines instantly when the data finally arrives.
It does, and it directly refutes the idea that WSC should be built entirely on so-called wimpy cores. You still need wide, out-of-order cores, the brawn, to efficiently handle those computational bursts.
Because if the core is too narrow,
If the core is too narrow, it handles the waiting periods just fine. But those 28% sprints become elongated. They stretch out. And that dramatically increases the tail latency we said was so critical.
So the nuanced conclusion is that wide cores are necessary, even if they're often used inefficiently during those long detented stalls.
That's the takeaway.
We've established that the back end, so the data stalls, is the primary bottleneck. Now let's circle back to the front end where the processor's fitting instructions. This is 4.1. The significant front-end bottleneck.
This is the second major architectural crisis that was highlighted by the profiling. Front-end bound cycles are persistently high. They range from 15% to 30% across the board.
That's much higher than normal.
That is 2 to 3 times higher than what you see in typical spec benchmarks. The core is constantly just waiting for instructions, even when the back-end execution units are theoretically ready to accept them.
And this starvation is severe enough that the processor's deep internal buffers can't hide it.
Exactly. Cycles where the core is completely starved due to front-end bottlenecks, where 0 microops are delivered, that typically exceeds 5% of all total cycles.
And this is happening even with modern architectures that have these deep instruction buffers, storing 40 or more instructions ahead of execution.
It is. This is really strong evidence of long latency instruction delivery events, most often caused by misses in the L2 instruction cache.
And the L2 instruction miss rates confirm this theory.
They are catastrophically high for these WSC workloads. They're often ranging from 5 to 20 MPKI. That's misses per kilo instruction.
And to put that in perspective,
That's an order of magnitude more frequent than the worst case instruction-heavy spec benchmarks. The front end is chronically starved because it just cannot get instructions quickly enough.
why are these modern, massive software stacks suddenly choking the instruction delivery system? That brings us to 4.2, massive and growing instruction footprints.
The core mechanical problem here is the nature of the WSC software itself. We already established that the binaries are huge, often hundreds of megabytes, and they lack clear repeating hotspots.
Right, the flat profiles.
Exactly. The code base is fundamentally lukewarm. The instruction caches are forced to deal with these large sets of instructions that are used occasionally, but they don't stay resident long enough to be useful on the next call.
And the shared L2 cache only makes this worse, I imagine.
It's the worst place for this pressure to build up because in the L2, those lukewarm instructions are competing for capacity directly with the massive data streams. The data stream constantly evicts the instruction stream, leading to perpetual instruction misses.
Let's put the size of this into perspective. How did these WSC instruction footprints compare to what was previously considered a huge benchmark?
Historically, the largest instruction footprint in the entire spec suite was 400.Perl bench, and that clocked in at about 172 kb.
Okay.
However, key WSC applications like Search2 and Bigtable were measured at over 4x that size, 688 kbb, and even higher.
And that size often exceeds the capacity of the L2 cache itself.
It does, which means instruction blocks have to be fetched all the way from the last level cache or even from main memory constantly. It's a huge latency penalty.
And the most alarming finding, the growth alarm, is that this problem is actively getting worse, not better.
It is escalating at a completely unsustainable pace. For a key service like Search2, the instruction working set increased by 27.77% per year over the 30 months they tracked it.
Almost 28% a year.
Per year. Think about the implications of that. Why is the code growing so fast? It's feature creep, it's highly complex C++ template usage, increased offensive programming, logging requirements. It all adds up.
And architects simply cannot keep up with that pace of growth by just making the instruction cache bigger every generation.
Exactly. A 27.77% yearly growth dramatically outpaces the typical rate of instruction cache size increases in new processor generations. Unless architects intervene in a radical way, the front-end bottleneck will become the dominant performance killer in future WSC systems.
And other workloads.
Some other critical workloads, like Bigtable, were more stable, but these core services are actively hemorrhaging instruction locality.
So given this crisis, what are the architectural solutions proposed in 4.3 for the instruction cache?
Well, the obvious solution is just make bigger instruction caches, but that consumes massive die area and it risks higher access latency, which kind of defeats the purpose.
Right, so what else?
So more complex instruction prefetchers are one route. You try to predict and pull code blocks into the cache before they're explicitly requested.
And what about the structural changes to the cache itself?
This is where we see proposals for some radical cache partitioning, especially in the mid-level caches. Designers must stop treating instructions and data as the same resource in the cache.
So you give instructions priority.
Specific proposals include modifying the replacement policies in the L2 to prioritize code over data, making those code blocks more sticky and harder to evict. But the most aggressive proposal is completely separate L2 instruction and data caches.
It's seen in some other chips.
Yeah, as chips like the Spark NS7 have implemented, this just acknowledges that the latency requirements for instruction fetch are paramount, even if it means sacrificing some of the flexibility of a unified cache.
So we have low IPC, high memory latency, and persistent instruction starvation. The core is powerful, but it's incredibly underutilized. How can we extract more work out of the available silicon? This brings us to 5.1, SMT efficacy in WSCs.
Simultaneous multi-threading, or SMT, often referred to as hyper-threading, is really the architectural gift that keeps on giving in this specific environment.
Why is it so effective here?
Since WSC applications have these complex inefficiencies in both the front end, where they're waiting for instructions, and the back end, where they're waiting for data, threads running on the same physical core are perfectly suited to complement each other's weaknesses.
So when one thread is stalled waiting for, say, a slow L3 instruction fetch, the other thread can jump in and utilize the execution units.
Precisely. The profiling under two wide SMT confirmed massive gains. Back-end efficiency improved immediately. Functional unit utilization, those ILP3 plus usage periods, increased from 28% up to 34%. SMT helped fill those necessary computational bursts.
And it provided relief for the instruction crisis, too.
Significant relief. SMT is excellent at absorbing those long latency fetch bubbles. The front-end bound cycles decreased significantly, dropping from a median of 22% down to 16%.
It's a big drop.
It is. Even the worst-case front-end starvation cycles dropped from 5% to 4%. SMT essentially buys the architect time to fix the underlying instruction cache crisis by hiding the latency.
However, SMT doesn't solve the core latency problem itself. It just papers over it.
No, it doesn't solve it. Even with two threads running, the total core throughput, the IPC, it effectively doubles. But 75% of the samples still showed an IPC of 1.2 or less per thread.
The underlying bottlenecks are still there.
The underlying latency bottlenecks, the L3 instruction fetch misses, and the main memory data fetch, they still persist. SMT hides the latency by context switching really rapidly, but it doesn't eliminate the actual wait time.
And this naturally leads us to 5.2, the need for wider SMT and specialized cores. If SMT helps hide latency so well, should architects simply increase the number of threads per core? Go from 2 to 4 or more?
The data strongly suggests that there's potential there. Since latency remains the primary bottleneck and memory bandwidth is not a constraint, the study really supports investigating wider SMT more than 2 threads per core.
Just stack more threads on.
You can stack additional threads on the core to ensure that those wide execution units are utilized while other threads are off waiting for some distant data access.
Let's synthesize all of these findings into the final blueprint for a future WSC architecture. What does it look like?
First, you have to avoid the wimpy core temptation. The system requires general-purpose, brawny, out-of-order cores to handle the diverse, bursty nature of the workloads. You need that power for the 28% of sprint cycles.
Okay, so powerful cores are a must. Second, you have to address that massive operational overhead.
You have to. You integrate dedicated, specialized accelerators for the 27% data center tax. This means specific hardware for RPC management, for protocol buffers, for compression. This is the cleanest, most direct way to cut down the overall computational costs of the WSC.
And the memory hierarchy needs a complete overhaul with a new focus.
We must trade bandwidth capacity, which we now know is over-provision, for latency reduction. This requires investment in faster cache access and critically aggressive instruction cache optimizations. We need partitioning or even total separation of instruction and data streams in the mid-level caches to manage those rapidly growing code footprints.
And the final, critical warning to the architects building these systems.
Do not use spec-ret results to guide your WSC processor design optimization. Focusing on throughput, on bandwidth, addresses a problem that doesn't exist in this environment. The empirical data from the live fleet confirms that latency is the real existential performance bottleneck.
This deep dive has fundamentally changed how we should understand the architecture of the warehouse-scale computer. For you, the learner, the key takeaways really redefine what efficiency means in the cloud.
First, the system's core challenge is extreme workload diversity. You cannot optimize for a single application anymore. You have to optimize for the common low-level functions that all applications share.
Second, those low-level functions, the data serialization, the RPCs, the compression, they create a massive, predictable 27% data center tax.
This is the unavoidable overhead of operating a distributed system, and it is the single best target for hardware specialization.
And third, the architectural pressure points are highly specific and often overlooked by conventional wisdom. Memory latency, not bandwidth, is the primary source of stalls.
And the instruction cache crisis, driven by those rapidly growing massive code footprints, is an immediate threat to future performance scaling.
That structural contradiction, that you need flexible, powerful, general-purpose cores, but you also need radical specialization to tackle the common overhead, that's the great balancing act for tomorrow's architects.
It is. They have to design systems that are both general and highly specific all at the same time.
And that leads to a provocative thought for you to explore on your own.
We've focused entirely on the large-scale server side, but your own desktop or your phone relies heavily on standard low-level routines, things like rendering, specific cryptographic processes, or network stack handling.
Right.
If we apply the logic of the data center tax to your client device, which low-level operations, currently handled inefficiently by software, might be the perfect candidates for low-power, dedicated hardware specialization to dramatically improve battery life or responsiveness.
So consider how much time your device spends on boilerplate work versus its unique application logic.
Exactly.
That's a deep dive that gives you the true insight into how the world computes. Thank you for joining us.